cation. So vitamin K plays an essential role in post-translational modification and allowing these enzymes to bind calcium. Warfarin, for many, many decades, the only oral anticoagulant, works by blocking this pathway, resulting in which one is unable to form fully functional clotting factors. So there's two ways of initiating the coagulation system in vitro. And again, this is the classic teaching. We're going to understand as we go the limitations to this model. But this is how the intrinsic pathway gets activated in vitro, which is the blood, the anticoagulated plasma gets exposed to a negatively charged surface. Originally it was glass, and now there's chemicals that are added to the mix that has a negative charge. The result of that is factor 12 can become activated using prekallikrein and high molecular weight kininogen, and we'll tease this out in a moment, resulting in factor 12A. So this is how the intrinsic pathway gets activated in vitro. This is the beginning of the PTT. The extrinsic pathway gets initiated by addition of tissue factor, a protein enmeshed in phospholipid. So the terminology intrinsic pathway comes from the fact that if you add plasma to glass, it will clot intrinsic to the blood. Nothing is required to be added for this activation to occur. The extrinsic pathway gets its name because you have to add something extrinsic to the sample, which is a mixture of tissue factor and phospholipid. And this is the beginning of the prothrombin time. So we're going to talk briefly now about the contact phase, which is the beginning of the intrinsic arm. So the contact system contains three factors: factor 12, prekallikrein, and high molecular weight kininogen. And these form a complex on a negatively charged surface, shown here, and it becomes a positive feedback loop where factor 12 gets converted by kallikrein to factor 12A. Factor 12A can convert prekallikrein to kallikrein. So you have this positive feedback loop, and high molecular weight kininogen serves as a cofactor for these reactions to occur. The factor 12A can, as I said, feed back to activate more prekallikrein, but also can convert 11 to 11A. And this is how the contact system initiates the intrinsic arm of the clotting system. At the other end, at the bottom of the clotting system, of the coagulation cascade, we have the protein fibrinogen. Fibrinogen is a complex multimer of 6 peptide chains, 2 alpha, 2 beta, and 2 gamma, shown here in cartoon form. And it's a long molecule with these D domains at the end here and an E domain in the middle. The way fibrinogen gets activated is an enzyme, physiologically it's thrombin, sequentially cleaves parts of the alpha and parts of the beta chain, releasing what's referred to as fibrin peptide A and fibrin peptide B, and that results in a fibrin monomer, which is able to polymerize. The fibrin polymer, the fibrin monomers, which polymerize, are then stabilized or cross-linked with factor 13A, shown here in cartoon form, and that results in a cross-linked stabilized fibrin clot. So that's how we see things at the bottom. And we've all learned about the D dimer, just shown here in different cartoon formats. These are only released when cross-linked fibrin is degraded by fibrinolysis, by enzymes that degrade fibrin, and we'll talk about that later on in the presentation. So if one sees elevated D dimer in a sample, that tells you that cross-linked fibrin has existed in the body. This could be from a clot, it could be from inflammation, it could be from a number of things, including cancer, but the D dimer simply tells us that cross-linked fibrin has formed in the body and been proteolyzed. So that's sort of the basics of the coagulation cascade as it's been understood for many, many years. But we've also recognized in the hematology world that this understanding of the coagulation cascade really has some major inconsistencies and gaps. So for instance, we look at the intrinsic pathway, and I'll show that again in a second, but some deficiencies in the intrinsic pathway are associated with severe bleeding, and other deficiencies do not cause bleeding at all. And one factor in the middle, factor 11, causes moderate bleeding. So how can all these enzymes in one pathway have different manifestations? We've also understood now that this concept of each factor is in a cascade where they're activated by the enzyme above and activate the enzyme below is also incorrect. And we'll talk about that. And we now know that some enzymes have multiple substrates and some factors have multiple means of becoming activated. So we're going to talk about this because I think this is key to understanding the coagulation system as a hematology expert, not as a medical student. So to get at this, we're going to talk about the cell-based coagulation model. Rather than that nice Y-shaped picture of Roman numerals, which seem to be in isolation, that's not how the real body works. So this is an illustration of a cartoon illustration of a enzyme substrate cofactor complex. So in green here is a illustration cartoon of a membrane. There's a cofactor that anchors the complex. There's an enzyme that forms part of the complex and a substrate. So each of these complexes in the coagulation system has a cofactor, enzyme, and substrate. And I call this enzyme 1 because it cleaves the substrate, which becomes a new enzyme, enzyme 2, and that will then work at the next stage of the clotting system. So we're going to talk about this a little bit. And here are 3 enzyme complexes that represent what's actually happening in key stages of the coagulation system. So we have the extrinsic 10-ACE, which is simply a complex of tissue factors to cofactor. Factor 7A is the enzyme, and factor 10 as the substrate. So this complex here of tissue factor, factor 7A, can then convert factor 10 to 10A. That's why it's called the extrinsic 10-ACE, because it cleaves 10 into 10A. In addition, there's the intrinsic 10-ACE, which uses factor 8A as the cofactor, factor 9A as the enzyme, and again, factor 10 as the substrate converting it to 10A. So this is where we've classically thought of the extrinsic and intrinsic pathways, each feeding in and activating 10, the beginning of the common pathway. And then you have factor 10, 10A as the enzyme of the prothrombinase complex, using factor 5A as the cofactor and prothrombin as the substrate. So this is shown here, factor 10A, 5A, and prothrombin as the substrate, and this is the common part of the clotting cascade. So understanding the cell-based mechanisms, the surface complex-based mechanism, helps put this Y-shaped schema into some biological sense. It doesn't fully explain everything, but we're getting there. So again, 3 key complexes you should remember: extrinsic 10-ACE, intrinsic 10-ACE, and the prothrombinase complex. Okay, now we're going to talk about the crossover, which starts to explain some of the gaps and misunderstandings. So, as I said a moment ago, the deficiencies of the contact system, factor 12, prekallikrein, and high molecular kininogen, even though they dramatically impact the partial thromboplastin time, do not result in bleeding. As a matter of fact, in the hematology world, it's famous that factor 12, named for Mr. Hageman actually died of a pulmonary embolism, not from a hemorrhage. Factor 11 deficiency is associated with a mild to no bleeding, but some of these patients will have mild bleeding, in particular post-surgery. And factor 8 and factor 9 deficiencies, the classic hemophilia A and hemophilia B, is associated with severe bleeding. So if 9 gets activated by 11 and 11 gets activated by 12, why would there be such a dramatic difference in severity based on the deficiencies of these factors? So to understand this, we have to now get the first real break from our concept of the classic coagulation cascade as a Y-shaped structure. Because reality is tissue factor 7A complex has two different substrates. We've all learned in the, studying the prothrombin time that this can activate 10, but in vivo, it also can activate factor 9, shown here. So tissue factor 7A activates 10 to 10A, but also can activate 9 to 9A. So this is the first example of sort of a crossover between the extrinsic and intrinsic arms. And so why is 9 important? Because if 10 can be activated directly, why would deficiencies of 9 or its cofactor 8 be clinically relevant? Well, what the key here is tissue factor pathway inhibitor, TFPI. And what we understand now is that in the body, TFPI dramatically blocks this reaction, dramatically reduces the ability of 7A to activate 10 to 10A, leaving its primary substrate in the body in vivo as factor 9. So this is what the coagulation system actually looks like. We have factor 7 theoretically has the ability to convert 10 to 10A. In vitro, it works fine, but in vivo, in the body, it's dramatically reduced. Therefore, the 7A tissue factor complex activates 9 to 9A, and using 8A as its substrate, this is how most of the coagulation activity occurs in the body. And that's why in the absence of 8 or 9, there's severe bleeding, even though theoretically this pathway could occur. This is exploited pharmacologically in that there's recombinant 7A available for patients with inhibitors to factor 8 or factor 9, and that will overcome this. But physiologically, this is what's actually happening in the vast majority of situations. And that explains why 8 and 9 deficiencies are severe, but 11 deficiency in the contact system is less relevant. So this is just showing the same concept again. This is what the real cascade looks like in the body. The next concept we want to talk about is the thrombin burst. And this is just some fun illustration of a burst, of a gamma burst from something exploding in space. Because this is going to address a lot more gaps. One of them is like, how does factor 5, 8, 11, 13 get activated in the classic cascade? And the answer is we don't know. But now we understand that there's a thrombin feedback, and we're going to talk about that. So the term thrombin burst is used to describe a dramatic augmentation of the coagulation system once some thrombin has been formed. And that's a series of positive feedback processes. And that's illustrated here. So here's thrombin formed, it's in gold. And rather than have all the arrows feeding back, which would make this illustration a mess, I'm just showing here with these horizontal arrows, all the different stages in the clotting system where thrombin feeds back to further activate clotting factors. So thrombin, or factor 2A, because prothrombin is 2, right? So thrombin is factor 2A, activates 11 to 11A, also activates the cofactors 5 and 8 to 5A and 8A, cleaves fibrinogen, which is its oldest known function, and also activates factor 13 to factor 13A, and that leads to cross-linking of the fibrin clot. So thrombin has a whole series of positive feedback contributions to the coagulation system. This also explains why patients with 11 deficiency have some bleeding, because 9 and 8 can get activated by 7A, as we talked about, but much of the without the role of factor 11, but factor 11 can be activated as part of a thrombin burst and feedback and further activate additional factor 9. So these are some of the activities, procoagulant activities, and In addition, I put it in brackets because it's not a clotting factor, but